Coordinated Universal Time, abbreviated as UTC, is the primary time standard by which the world regulates clocks and time. It is, within about 1 second, mean solar time at 0 degrees longitude. It does not observe daylight saving time. It is one of several closely related successors to Greenwich Mean Time. For most purposes, UTC is considered interchangeable with GMT, but GMT is no longer precisely defined by the scientific community. UTC was officially formalized in 1960 by the International Radio Consultative Committee in Recommendation 374, having been initiated by several national time laboratories. The system was adjusted several times until leap seconds were adopted in 1972 to simplify future adjustments. A number of proposals have been made to replace UTC with a new system that would eliminate leap seconds, but no consensus has yet been reached. The current version of UTC is defined by International Telecommunications Union Recommendation Standard Frequency and Time Signal Emissions and is based on International Atomic Time with leap seconds added at irregular intervals to compensate for the slowing of Earth's rotation. Leap seconds are inserted as necessary to keep UTC within 0.9 seconds of universal time, UT1. See the current number of leap seconds section for the number of leap seconds inserted to date. Etymology. The official abbreviation for Coordinated Universal Time is UTC. This abbreviation arose from a desire by the International Telecommunication Union and the International Astronomical Union to use the same abbreviation in all languages. English speakers originally proposed CUT, while French speakers proposed TUC. The compromise that emerged was UTC, which conforms to the pattern for the abbreviations of the variants of universal time. Uses. Time zones around the world are expressed using positive or negative offsets from UTC, as in the list of time zones by UTC offset. The westernmost time zone uses UTC-12, being 12 hours behind UTC. The easternmost time zone, theoretically, uses UTC+12, being 12 hours ahead of UTC. In 1995, the island nation of Kiribati moved those of its atolls in the Line Islands from UTC-10 to UTC+14 so that the country would all be on the same day. UTC is used in many Internet and World Wide Web standards. The Network Time Protocol, designed to synchronize the clocks of computers over the Internet, encodes times using the UTC system. Computer servers, online services and other entities that rely on having a universally accepted time use UTC as it is more specific than GMT. If only limited precision is needed, clients can obtain the current UTC from a number of official Internet UTC servers. For sub-microsecond precision, clients can obtain the time from satellite signals. UTC is also the time standard used in aviation, e.g., for flight plans and air traffic control clearances. Weather forecasts and maps all use UTC to avoid confusion about time zones and daylight saving time. The International Space Station also uses UTC as a time standard. Amateur radio operators often schedule their radio contacts in UTC, because transmissions on some frequencies can be picked up by many time zones. UTC is also used in digital tachographs used on large goods vehicles under EU and AETR rules. Mechanism. UTC divides time into days, hours, minutes and seconds. Days are conventionally identified using the Gregorian calendar, but Julian day numbers can also be used. Each day contains 24 hours and each hour contains 60 minutes. The number of seconds in a minute is usually 60, but with an occasional leap second, it may be 61 or 59 instead. Thus, in the UTC time scale, the second and all smaller time units are of constant duration. but the minute and all larger time units are of variable duration. Decisions to introduce a leap second are announced at least 6 months in advance in Bulletin C, produced by the International Earth Rotation and Reference Systems Service. The leap seconds cannot be predicted far in advance due to the unpredictable rate of rotation of the Earth. Nearly all UTC days contain exactly 86,400 SI seconds, with exactly 60 seconds in each minute. However, because the mean solar day is slightly longer than 86,400 SI seconds, occasionally the last minute of a UTC day is adjusted to have 61 seconds. The extra second is called a leap second. It accounts for the grand total of the extra length of all the mean solar days since the previous leap second. The last minute of a UTC day is permitted to contain 59 seconds to cover the remote possibility of the Earth rotating faster, but that has not yet been necessary. The irregular day lengths mean that fractional Julian days do not work properly with UTC. Since 1972, UTC is calculated by subtracting the accumulated leap seconds from International Atomic Time, which is a coordinate timescale tracking notional proper time on the rotating surface of the Earth. These discontinuities take the form of leap seconds implemented by a UTC day of irregular length. Discontinuities in UTC have occurred only at the end of June or December, although there is provision for them to happen at the end of March and September as well as a second preference. The International Earth Rotation and Reference Systems Service tracks and publishes the difference between UTC and Universal Time, DUT1 equals UT1 UTC, and introduces discontinuities into UTC to keep DUT1 in the interval. As with TI, UTC is only known with the highest precision in retrospect. Users who require an approximation in real time must obtain it from a time laboratory, which disseminates an approximation using techniques such as GPS or radio time signals. Such approximations are designated UTC, where K is an abbreviation for the time laboratory. The time of events may be provisionally recorded against one of these approximations. Later corrections may be applied using the International Bureau of Weights and Measures monthly publication of tables of differences between canonical TI UTC and TI UTC as estimated in real time by participating laboratories. Because of time dilation, a standard clock not on the geoid, or in rapid motion, will not maintain synchronicity with UTC. Therefore, telemetry from clocks with a known relation to the geoid is used to provide UTC when required, on locations such as those of spacecraft. It is not possible to compute the exact time interval elapsed between two UTC timestamps without consulting a table that describes how many leap seconds occur during that interval. Therefore, many scientific applications that require precise measurement of long intervals use TI instead. TI is also commonly used by systems that cannot handle leap seconds. GPS time always remains exactly 19 seconds behind TI. For most common and legal trade purposes, the fractional second difference between UTC and UT is inconsequentially small. Greenwich Mean Time is the legal standard in Britain during the winter, and this notation is familiar to and used by the population. Time zones are usually defined as differing from UTC by an integer number of hours, although the laws of each jurisdiction would have to be consulted if sub-second accuracy was required. Several jurisdictions have established time zones that differ by an integer number of half-hours or quarter-hours from UT1 or UTC. Current civil time in a particular time zone can be determined by adding or subtracting the number of hours and minutes specified by the UTC offset, which ranges from UTC-1200 in the west to UTC plus 1400 in the east. The time zone using UTC is sometimes denoted UTC plus or minus 000 or by the letter Z, a reference to the equivalent nautical time zone, which has been denoted by AZ since about 1950. Time zones were identified by successive letters of the alphabet, and the Greenwich time zone was marked by AZ as it was the point of origin. The letter also refers to the zone description of 0 hours, which has been used since 1920. Since the NATO phonetic alphabet word for Z is Zulu, UTC is sometimes known as Zulu time. This is especially true in aviation, where Zulu is the universal standard. This ensures all pilots, regardless of location, are using the same 24-hour clock, thus avoiding confusion when flying between time zones. See the list of military time zones for letters used in addition to Z in qualifying time zones other than Greenwich. On electronic devices that only allow the current time zone to be configured using maps or city names, UTC can be selected indirectly by selecting Reykjavik, Iceland, which is always on UTC and does not use daylight saving time. Daylight saving time UTC does not change with a change of seasons, but local time or civil time may change if the time zone jurisdiction observes daylight saving time. For example, local time on the east coast of the United States is 5 hours behind UTC during winter, but 4 hours behind while daylight saving is observed there. History. At the 1884 International Meridian Conference held in Washington, D.C., the local mean solar time at the Royal Observatory, Greenwich in England, was chosen to define the universal day, counted from 0 hours at mean midnight. This agreed with civil Greenwich Mean Time, used on the island of Great Britain since 1847. In contrast, astronomical GMT began at mean noon, 12 hours after mean midnight of the same date until the 1st of January 1925, whereas nautical GMT began at mean noon, 12 hours before mean midnight of the same date, at least until 1805 in the Royal Navy, but persisted much later elsewhere because it was mentioned at the 1884 conference. In 1884, the Greenwich meridian was used for 2/3 of all charts and maps as their prime meridian. In 1928, the term universal time was introduced by the International Astronomical Union to refer to GMT, with the day starting at midnight. Until the 1950s, broadcast time signals were based on UT, and hence on the rotation of the Earth. In 1955, the cesium atomic clock was invented. This provided a form of timekeeping that was both more stable and more convenient than astronomical observations. In 1956, the U.S. National Bureau of Standards and U.S. Naval Observatory started to develop atomic frequency time scales. By 1959, these time scales were used in generating the WWV time signals, named for the shortwave radio station that broadcast them. In 1960, the U.S. Naval Observatory, the Royal Greenwich Observatory, and the UK National Physical Laboratory coordinated their radio broadcasts so time steps and frequency changes were coordinated, and the resulting time scale was informally referred to as Coordinated Universal Time. In a controversial decision, the frequency of the signals was initially set to match the rate of UT, but then kept at the same frequency by the use of atomic clocks and deliberately allowed to drift away from UT. When the divergence grew significantly, the signal was phase-shifted by 20 milliseconds to bring it back into agreement with UT. 29 such steps were used before 1960. In 1958, data was published linking the frequency for the cesium transition, newly established, with the ephemerosecond. The ephemerosecond is the duration of time that, when used as the independent variable in the laws of motion that govern the movement of the planets and moons in the solar system, causes the laws of motion to accurately predict the observed positions of solar system bodies. Within the limits of observing accuracy, ephemeroseconds are of constant length, as are atomic seconds. This publication allowed a value to be chosen for the length of the atomic second that would work properly with the celestial laws of motion. In 1961, the Bureau International d'Hour began coordinating the UTC process internationally. Time steps occurred every few months thereafter, and frequency changes at the end of each year. The jumps increased in size to 100 ms. This UTC was intended to permit a very close approximation to UT2. In 1967, the SI second was redefined in terms of the frequency supplied by a cesium atomic clock. The length of second so defined was practically equal to the second of ephemeris time. This was the frequency that had been provisionally used in TI since 1958. It was soon recognized that having two types of second with different lengths, namely the UTC second and the SI second used in TI, was a bad idea. It was thought that it would be better for time signals to maintain a consistent frequency, and that frequency should match the SI second. Thus it would be necessary to rely on time steps alone to maintain the approximation of UT. This was tried experimentally in a service known as stepped atomic time, which ticked at the same rate as TI and used jumps of 200 milliseconds to stay synchronized with UT2. There was also dissatisfaction with the frequent jumps in UTC. In 1968, Louis Essen, the inventor of the cesium atomic clock, and G.M.R. Winkler both independently proposed that steps should be of 1s only. This system was eventually approved, along with the idea of maintaining the UTC second equal to the TI second. At the end of 1971, there was a final irregular jump of exactly 0.107758 TI seconds, so that the 1st of January 1972 0 hours 0 minutes and 0 seconds UTC was the 1st of January 1972 00:0010 TI exactly, making the difference between UTC and TI an integer number of seconds. At the same time, the tick rate of UTC was changed to exactly match TI. UTC also started to track UT1 rather than UT2. Sometimes signals started to broadcast the DUT1 correction for applications requiring a closer approximation of UT1 than UTC now provided. Current number of leap seconds. The first leap second occurred on the 30th of June 1972. Since then, leap seconds have occurred on average about once every 19 months, always on the 30th of June or the 31st of December. As of July 2015, there have been 26 leap seconds in total, all positive, putting UTC 36 seconds behind TI. Rationale: Earth's rotational speed is very slowly decreasing because of tidal deceleration. This increases the length of the mean solar day. The length of the SI second was calibrated on the basis of the second of ephemeris time and can now be seen to have a relationship with the mean solar day observed between 1750 and 1892, analyzed by Simon Newcomb. As a result, the SI second is close to 1/86,400th of a mean solar day in the mid-19th century. In earlier centuries, the mean solar day was shorter than 86,400 SI seconds, and in more recent centuries it is longer than 86,400 seconds. Near the end of the 20th century, the length of the mean solar day was approximately 86,400.0013 s. For this reason, UT is now slower than TI by the difference of 1.3 milliseconds day. The excess of the load over the nominal 86,400 s accumulates over time, causing the UTC day, initially synchronized with the mean sun, to become desynchronized and run ahead of it. Near the end of the 20th century, with the load at 1.3 milliseconds above the nominal value, UTC ran faster than UT by 1.3 milliseconds per day, getting a second ahead roughly every 800 days. Thus, leap seconds were inserted at approximately this interval, retarding UTC to keep it synchronized in the long term. The actual rotational period varies on unpredictable factors such as tectonic motion and has to be observed, rather than computed. Just as adding a leap day every 4 years does not mean the year is getting longer by 1 day every 4 years. The insertion of a leap second every 800 days does not indicate that the mean solar day is getting longer by a second every 800 days. It will take about 50,000 years for a mean solar day to lengthen by 1 second. This rate fluctuates within the range of 1.7–2.3 milliseconds (psi), while the rate due to tidal friction alone is about 2.3 milliseconds (psi). The uplift of Canada and Scandinavia by several meters since the last ice age has temporarily reduced this to 1.7 milliseconds (psi) over the last 2,700 years. The correct reason for leap seconds, then, is not the current difference between actual and nominal LOD, but rather the accumulation of this difference over a period of time. Near the end of the 20th century, this difference was about 1/800th of a second per day. Therefore, after about 800 days, it accumulated to 1 second. In the graph of DUT1 above, the excessive LOD above the nominal 86,400 s corresponds to the downward slope of the graph between vertical segments. Because of a slight acceleration of Earth's crust temporarily shortening the day, vertical position on the graph corresponds to the accumulation of this difference over time, and the vertical segments correspond to leap seconds introduced to match this accumulated difference. Leap seconds are timed to keep DUT1 within the vertical range depicted by this graph. The frequency of leap seconds therefore corresponds to the slope of the diagonal graph segments, and thus to the excess LOD.